is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey, welcome to Skytour Livestream. It's I, Mark Antonio, your, what's the word? Concierge to the stars, or something like that, right? That's something crazy. I want to welcome Daryl Mason. Daryl, how you doing?
Hello, Mark. I'm good. You?
All right,
Hi, everybody.
thank you. I'm doing fine. Good to see you here. Tonight we're finishing off. Well, we're starting off tonight with one of the last summertime objects that we can see in the sky, and that's the northern Cygnus region of where the North American Nebula is, and this here, the Pelican Nebula that we're seeing right in front of us. The Pelican Nebula is a diffuse nebula region. It's a region where stars are being formed, and stars are also responsible for lighting up this whole region. Here you can see our nomenclature. The Pelican Nebula is here. Some of the brighter stars are noted, and we have a star cluster over here known as NGC 6997. Let's see if we can actually pull the telescope out there so you can see this a little better. There we go. And I'll minimize this right now. So there you go. So now you actually see where we are in the sky. Here's the Pelican Nebula itself. This bright area here is an area of the Pelican where there's two ways that people look at this. They look at this and say, oh, it's looking three-dimensional. Yes, that's one thing that you can say, and maybe it looks that way to you, but there's another possibility for why it looks this way. And that possibility has to do with density of the gas. If the gas is denser over here, then the nebula will indeed appear brighter red here, which gives the illusion of three-dimensionality. But it could be just denser gas plowed by hot solar, stellar radiation from over here pushing this way. And sure enough, we know that happens in some of these nebulae. There's some beautiful dark lanes in here. All right, and this image is actually not a frozen image. It's developing before our eyes. I just have an overlay showing you all these things here. So if we actually get rid of the overlay, all right, now we're back to looking at this beautiful live image coming in. And I will add a couple things here to help make it look good. I'm going to go to my enhancement tab here. And I'm going to add a little bit of something called color noise reduction. That's going to help get rid of a lot of the modeling that we see. And notice how much better it already looks. I don't know if you can see that, but it is better. And then the other thing I'm going to do is I'm going to add an unsharp mask to this whole equation, which allows us to sharpen up areas of the image. And now you can see all this really subtle detail. It's very dramatic. You see all this subtle detail in here. So it's really cool. I do want to say hello to Tim F., who was number 1 today. Yay, Tim. Lubo in China is with us. Hey, Lubo. It's got to be the afternoon over there. Michael Hedrick's with us. Nice to see you. Elise, hey, how you doing? Nice to see you. Thank you. She says, pretty cool, Mark. Yeah, it is cool. It is cool. And I'm running it from 2,000 miles away. So it's kind of cool. Papa Tom's with us. Hey, Papa Tom. Papa Tom, I haven't forgotten your offer. We'll talk about that. Mind Forked. That's Chris. Hey, Chris. How you doing? Counting down the months, Chris. We'll be seeing each other again at the Palm Springs Indian Wells Conference. And then, of course, we have GLGM 1159. Hey, Happy New Year to you, man. Thanks for joining us. If you haven't subscribed, do that. It's free. You get to see these images. You actually download these images for nothing. But to do it, you go here. You go to skytourlive.org, and that's our entry portal into all of our data. And you read the instructions. It tells you how to get it. And you can download images just like this one and put them on your computer for no charge. We do process these very highly later. And if you're a subscriber, and even if you want to take it a step further, become a member of the Patreon, then you can get these very, very highly processed images. So it's pretty cool. And I would hope that some of you might consider doing that. Stuffy's with us. How you doing? Yeah, Christmas was great, thank you. New Year is starting off well, I think. And we got Creeptasia's with us. How you doing, Creeptasia? Let's see. So I'll say hello also to you, Daryl. I think I said hi to you.
You did.
Okay, cool. And then
An interesting little, very thin, dark line.
This one?
Sort of it. No, much farther down.
Oh, okay.
It's like at the bottom of the where the pelican's beak is meeting his chin.
This here?
Farther up, right? Just up a little bit to the right.
Okay, talking about this little area right there.
Yeah.
Well, always zoom in on that and check it out. We have 20 exposures so far, so the data will stand zooming in quite a bit. Look at that. Look at that. That's pretty cool. Look at that little thing. These dark tendrils are interesting. I just did I don't know if you saw the post, guys, on Facebook, but I actually talked about this interstellar dark dust that we see, kind of where it comes from, what it's made of. You'd be surprised how complex it is. But once you read that post, it'll show you why all life depends on it. And in fact, the way it's composed, the composition, it's everything from methanol to formaldehyde ices, ammonia ice, water, carbon dioxide ice. And it goes onto the surface of a silicate or carbon dust grain. And those dust grains come from supernovae, all right? And you can't have ice on supernovae particles, of course, because they're too hot. But as they cool and become distanced from the supernova location, like this chunk has, then you have the ability for these the condensates, or the condensation of these particles like this to occur, and they will on their surfaces they will be a beautiful, catalyst location for ices to form in the depths of space where it's nice and dark. And the more dust we have, the more protection from ultraviolet radiation we have. So stars like this, for instance, young hot stars, they could easily render any nearby planetary areas sterile, and might not even allow an atmosphere to form around such a planet. But if that planet was formed inside of one of these dark nebulae, then that ultraviolet radiation would be effectively stopped, depending on how dense it is, of course. And that would allow for planets to form inside a nebula. Now, if you were in there, you might just see the universe out there and not really know what the extent of the universe was. However, there's a lot of these regions. Now, we see all this dark dust. This is dark dust. Everywhere we look, we see dark dust. But keep in mind, we're looking within our galaxy. And dark dust is something that is characteristic of galaxies. Yes, there's 2 trillion potential galaxies out there. However, this dark dust, for all of its presence in all of these galaxies in one way or another, most of them, okay, not the ellipticals, but in the spiral galaxies and barred spiral galaxies where we see this, dust only comprises about 1% of the interstellar medium. 1%. But that 1% is extremely important, because you come from that. We come from that. Earth comes from that. Every planet in our solar system, every asteroid comes from that 1%. So you can see that if we had just increased the percentage of dust in the universe by 0.5%, then the universe would be an incredibly more dusty place. Unbelievable. So there's a lot going on in these nebulae right here that we're seeing. But if you haven't had a chance to read my discussion of this dark dust that we see throughout our imagery, it's on Facebook. It's on a number of different astronomy sites, actually. But you can find it on our SkyTour livestream Facebook site. You can find it on my personal Facebook site. So go check it out. There's a diagram also of a dust grain, that minuscule, tiny, tiny particle, a micron in size or less, of these particles that accumulate these ices. And you learn about what these are. And what they are the building blocks of life. You get really long chains of molecules on them. And of course, we know that long chains of molecules are something that we love to see with organic chemistry. And we see a lot of that. We get hydrocarbons. It's incredible. Now, Stephen A. in the chat, welcome, by the way, and welcome to you, a rock star. I didn't say hi to you, sorry. He asked, what held everything together? Excellent question. And at first glance, you might wonder if it's just going every which way. What's holding it together? What's holding it together is the mass of the particles themselves, because they lead to a gravitational field. And that allows them to gravitationally and mutually condense toward each other. If you have 2 particles out in space with nothing anywhere near it, light years away, but you have 2 particles that weigh only a thousandth of a gram apiece, and you separate them by a mile, slowly they will attract to each other, because as far away as they are and as tiny of a measurement of mass as they have, there is a mutual gravitational attraction between them. And over time, which the universe has in abundance, those particles will attract to each other and connect. And when they do, they'll be now twice as large. And any other particles nearby will then be attracted all the more strongly. And that will continue and will cascade and domino effect into very, very large objects accumulating quite quickly on the universal scale anyway. So that's what's cool. Now we've actually got 33 of these stacked. Let's back out here and see what it actually looks like now. There it is.
Marianne is here.
Marianne's with us. Hey, Marianne. Marianne said she might drop in. It's nice to see you, Marianne. As those of you watching, when you see SkyTour live stream, you have to thank Marianne. In the chat, she's listed as Marianne Robb. She and Tara were responsible for everything you see. I'm just the astronomer, okay? It was my idea in the beginning, and then Marianne and Tara said, hey, this would really be cool as something that we show to lots of people. And then Bill Skywatcher and Keith from P&K Space Imaging, they encouraged me to start streaming. And that's why I'm doing what I'm doing. I never would have done this. I never would have thought about the possibility. And right now, I'm doing something else. I've got a couple cameras on the way, and we're actually building a full-color, high-resolution, all-sky camera. And right now, when we come up here in the menu here, you can just barely see it, but right above here, there's a menu called Camera. And in here, there's a list of cameras. Some are simulators, some are not. And we're currently in this one, the ASI 183 MC Pro. That's this camera that's got all its parameters here. This is called a ZWO camera. ZWO is the actual the make of the camera. Well, all we're going to have to do is select the new all-sky camera in here, and that'll allow us to see the all-sky view. However, there's another thing we can do. We can have two instances of this program running. So in the background, we have this program, and then in the background we're going to have a similar sized view, full color, very high resolution in 4K, and it's going to be a beautiful image of the night sky in real time. And the camera is going to record all night long, and it's going to build a time lapse every single night showing what happened the previous night. Then it's going to build another couple of diagrams that will help help you look at the weather for the night. And it even has overlays, so you could actually bring up the stars that you're looking at in the same way that we see when we do this. Okay, and we see our overlays. We're going to see that at a much less detailed level. You see the star names and so forth, little plus signs indicating where they are. It's pretty cool. So it'll be really cool. Now, as Daryl says, if you like it, hit that thumbs up. Okay, we need it. We're a nonprofit organization, and when we say nonprofit, we mean it. We're not making a whole lot of money at all. We would need a lot of more Patreon subscribers. We actually have another telescope going in out in Arizona, and that's one that I'm going to be going out there in, later in January here. It looks, hopefully, if not that, early February, to study some locations where we'll be putting another telescope. And I've got a design for an enclosure. It's not going to be a whole building. It's going to be just a little enclosure that opens with linear actuators and allows the telescope to be in there. So it's going to be very nice, and hopefully it'll be a easy implementation. I learned everything doing this one. So any further implementations of doing this remote kind of work should not be nearly as big a deal and might actually be a lot easier. Now, if you have any questions, do put them in. I saw Stephen A. asked another. He says, I can't wait, and I just got here. Well, Steven, thanks, man. Do subscribe, okay? And again, if you guys have if you're thinking about it, you might want to go here too, up there in the upper right corner. Go to Sky Tour Shop on Etsy. All our photographs are emblazoned on cups, on mugs, mouse pads, bedspreads. We have tons and tons of these beautiful, highly processed photos. And talk to the people in the chat, because there's people in the chat that have bought them. And they have been quite blown away by the quality, as have I. Really impressive stuff. Travel mugs that have your favorite nebula on it. I just think it's so cool. You know, remind you of the universe that awaits you. You know. Hey, Bonnie. I didn't see that Bonnie arrived, but I guess she did.
She did.
All right.
Hello, Bonnie.
Yeah. Yep, yeah.
Marianne has a question of you.
Oh, she does?
Right down at the bottom.
Oh. Oh, yeah. Sorry. I mentioned it before, Marianne. I apologize. This is the Pelican Nebula. If you look where the telescope is pointing, which you can't see because I've got this up. Let me just move this out of the way for a second. Okay. If you look where the telescope is pointing, it's actually pointing way over to the west, northwest. Okay. This is a summer sky object. This is the Pelican Nebula in Cygnus the Swan, a true summer constellation, part of the summer triangle of Deneb, Vega, and Altair. And this is a diffuse nebula. This dark stuff in between is not a void in the nebula. It's actually dark nebula in the way of the nebula behind it. Okay, so that's pretty cool. And you know, seeing this with spectra, you know, when I take spectra of these regions, and with radio telescopes, we can clearly see that it's foreground dust we're looking at. You know. Hey, Tess Larico, how are you? Welcome. Thank you for the well wishes. It's first time here. Okay, everybody in chat, let Tess know what it's going to be like to hang out with us here, because I have a feeling people are going to really want to share their experiences with you, Tess. You know, we've got thousands of people that are free subscribers. You can be one too. Please do. And she's talking about, Tess is talking about, it's about to explode. Well, I mean, depending where comets are, if they get close to the sun, sometimes they theorize that they could break apart, yes.
I suspect she's talking about Comet Pons-Brooks.
Yeah, that's the one that you asked about the other night, too. Yeah.
I'm about to find out.
Okay. While you're doing that, I'll answer Michael Hedrick's question. He says... first of all, Steven says, been subdued for a while, but never been to a live one. Now you are, man. I hope you love it, man, because we do too. Go ahead.
I'm sorry. The Devil Comet is indeed Comet Pons-Brooks.
Okay.
Which is very low over in the west-northwest after sunset.
Yeah.
It's below the wall for the observatory. We can't see it with the telescope.
Yeah.
But they're calling it the Devil's Comet. It's been tending to put off massive flares about every 15 days.
Oh, that's right. That's what Tess was referring to. You're right, Tess. It's flaring.
It's about due to do it again, if it hasn't already.
Now, when people say, what are these flares? Well, comets are not hot, okay? They're actually very cold objects, and a slight difference in temperature because of the sun's heating on one side of the comet, they rotate, okay, will cause what's called outgassing. And material and gas trapped below in the ice, as that ice sublimates away, it doesn't melt like water melting on a pond full of ice. It sublimates. It goes, directly from ice to a gas. And when that happens, it could release more gas that's trapped in the ice. And when that happens, you see jets coming off. Comets are very well known for having these jets. And they're actually called cometary jets. And that can sometimes cause the comet to spin differently, because some of these comets are not, they're not, none of them are thousands of miles across. Most of them are just like a few kilometers in size. 3 to 12 kilometers in size. Is really not very big, or smaller. And every time they go around the sun, a little bit more of them evaporate. So eventually they get down smaller and smaller and smaller. And they don't just go away at the end either, because the cometary ices that are around the comet or on the comet typically seed, S-E-E-D, seed around a core of rock. And so when we talk about dead comets, which we'll do sometimes, you'll find we're talking about a very dark object where all that ice has evaporated away for the most part, and there's only mild signatures left of its past cometary existence. So comets do these jets quite frequently. Yeah. I wanted to find out, there was another question too. Oh, I was Michael Hendricks. I was going to answer this before. Sorry, Mike. Jupiter's volcanic moon Io. Does erosion cause the height if it's volcanoes, or is the height of all the volcanoes uplifting? Okay, volcanic uplifting. Well, Io's a bit strange. Okay, Io is, think of it as Io as a rubber ball. It's being squished all the time as it goes around Jupiter. It's being tugged on by Europa. It's being tugged on by Ganymede and Callisto. Ganymede's the biggest moon in the solar system. Okay, and it's actually it's pretty much planet-sized. Okay, but the gravitational pull from all those other Galilean satellites needs, like bread, needs Io and squishes it and makes it come back to shape. And as it does, it heats up the core. Io's got a lot of sulfur content, and so we see volcanic eruptions of molten sulfur and geysers of sulfur. We see sodium atoms in the atmosphere of Io, which actually has an atmosphere. When it's on the front side of Jupiter and it's got sunlight on it, it has a very tenuous atmosphere. Then when it goes around to the dark side of Jupiter, it rains out like snow and goes down to the surface. And then when it comes around the daytime again, it goes back into the now atmosphere that returns. It's a very strange location. Thank you, Tess. That was very kind. Thank you so much. Desert Dweller, hey, how you doing? Good to see you. Okay, this is where we're going to stop with this guy. This again is the Pelican Nebula. I've got it defined up there. Now, when we hit save here, I'm gonna dock this up again. I didn't sure, and Daryl and I talked about this. We weren't sure we were going to be able to do this tonight because it's not. It's kind of in and out clear, but we're taking advantage of it. We're experienced enough to know that this slight cloudiness around the stars shows that we're photographing this through extremely light cloud cover. But if you notice, it's still beautiful. In fact, when we have this kind of light cloud cover, many of these images look like pieces of art when we're done. It just looks stunning. Okay, so what I'll do is I'll save it now. And the first save, as you notice, the green bar up there, I know it's hard to read, but it's going to save it as a .fits, a .fits file. Well, the FITS file is a file that is an astronomical file format. Now you might say, oh, I don't know what that is. And you don't have to worry about it, because the next save I do is save exactly as seen. So now what you get, I'll show you exactly. I'm going to click on it. There it is. And bring up the image. Okay. Let that come in. There you go. That's what you got on the server. Now, when I say server, that's something else. When we photograph everything and we save it, it leaves our observatory out in the desert, goes up to the cloud, and it ends up on our server that you can reach. How? By going to skytourlive.org and going down to the dark gray panel just underneath that main panel. It'll allow you to get to all of our images.
Or I just posted a link to the server.
And that's our Daryl. Thank you very much. That's right.
Yeah.
Daryl's been doing this with us for a couple years now, haven't you? It's been 2 years or more.
much more.
Yeah, right? Yeah, I'm really not sure.
2017, if not 2016.
Wow. Yeah, we've been doing this for a while. Yeah. Okay, gonna go back to our. I have a low light mode that we go into with the camera when we're in between shots, so you can actually see what the sky looks like. So that's this mode here. That nebula is hiding in this image. You just don't see it. You know. However, our telescope systems know where everything is, regardless. And what I'm going to do now is save this image with the annotations as well. And I might be able to just come into the stack and bring the stack up again. It might still be there. Let me get rid of this. Yeah. And now I can save it again. And so now this annotation will be out there. So if you want to know what we looked at, well, this imagery will be there for you to look at. And you could download this as well. So we're saving this image with the annotations. All right. And that's the reason why I don't clear the stack right away. When I say stack, what am I talking about? Well, we take a picture, and then we take a second picture, and we align it with the first. Line up all the stars, and then we stack that on top. And we just make an image sandwich. And that image sandwich brings this very tiny, dark stuff into view very, very clearly, because all the data that belongs there goes to the top. And stuff that doesn't belong there, like random noise, gets wiped out over time. It's really a beautiful, elegant process. All right. Now we'll go back to our night vision mode here. Okay. All right. So now the telescope really whipped all the way around to get here. So when I go to another thing, it's gonna whip under the pole, and it's gonna look really strange, and it's gonna look like it's not working right, but it is. All right. And let's go to the other side here. Let's go up to Auriga. And let's see if we can let's go to Capella right now, the bright star Capella. So if you watch the telescope, it's going to do something strange. I don't mind telling you, it scared me. Because I thought, oh no, look at the telescope. It's like going the wrong way. But that's the mount. And as it spins around, it's unwinding the cables that were tangled. And I'm hoping that it'll continue to be untangled. If it doesn't, well, then we'll have to do a maintenance visit, but haven't had a problem yet with that. Okay, that's the back end of the scope. This gives you a chance to see the guide scope. That's the guide scope on top of the telescope right there. And the camera is actually inside this front shroud. It's stuck on the front of the telescope because we converted this telescope from a regular telescope that looks at the sky, has very, very high magnification, to a telescope that now has, it runs much faster. It runs 25 times faster than previous scopes. There's Capella. And it's running at a photographic speed, for those that are photographers, of f2. So that means it's going really, really fast. Okay. So we'll just wait for there it is. Okay. Hey, old school, how you doing?
Desert Dweller has a question of you.
Okay. And Renee Barnett is here. Renee actually got one of our Sky Tour Shop gifts. Renee, tell everybody what you thought of it. Desert Dweller says, may I ask, what's the furthest object you viewed? That's a matter of resolving power, and something called the Dawes limit comes into play there. And it's basically aperture. The bigger the aperture, the farther you can see. We have a 10-inch aperture on this telescope. And what we could do is we've seen things that are magnitude 18. Now, what's that mean to you? It means very faint. So it's brightness. Now, the farther away things are, the dimmer they are. We've seen galaxies that are 80 million light years away and more. I think one night we looked at a galaxy that was 130 million light years away. You know, it means 130 million years ago, the light we see tonight left that galaxy to come here. went all the way across intergalactic space, then went into our galaxy, into our planet. When it left that galaxy, it was 130 million years ago. The dinosaurs were still here when it left. In fact, they were right in the middle of their heyday 130 million years ago. So the universe is big, in other words, you know. So that's what I think. Cindy Murphy's with us. Hey, Cindy Murphy says, I got a mug with Pleiades and I love it. Thanks for letting everybody know. I forgot, I didn't see you here, but I'm glad you're here. So yeah, so people in the chat have bought some of these things. Cindy also got one of our giant blankets. So tell people about that blanket, Cindy, if you will, too. Again, Etsy shop, it says Sky Tour shop is in the upper right corner there. You know, we operate on you know, the funds that people give us and do for us, and that's what matters. You know, we're trying hard. So let's see now. Okay, this is Capella, and what I'm going to do is I'm going to center Capella in here, and I'm going to then I'm going to make sure that our telescope alignment is good. After you switch under the pole like that, you got to be careful. So that's what I'm going to do now. Okay, we're going to bring Capella. Capella, you know, Daryl's really good with the mythology. So we're in the constellation Auriga right now. So Daryl, not to put you on the spot, but tell folks about Auriga and the history of Auriga before we start deciphering some of the objects that are here.
Auriga is the charioteer. It represents a man driving a chariot. Capella is the bright star at his left shoulder, it would be to our right. Capella has sort of Auriga has sort of a hexagon shape. Capella is his left shoulder on our right as we look up in the sky. Capella is known as the goat star, G-O-A-T, goat, you know, like bah. It's a very old name, goes back thousands of years. But it's called the goat star, and if you see there, he's holding a goat in his left arm. And if you look closely there at the stellarium, those three little triangles, those three little stars in a triangle just to the upper right of Capella, those are called the kids. And he's holding three baby goats in his arm. And the big goat is Capella.
These are the kids.
Yeah. Now, why a charioteer is carrying a goat, you got me.
I don't know.
But he is.
He's outrunning the Roman army. I don't know. Or the Greek army. Yeah, that's cool. Thank you, Daryl. And so, and that's a nice thing, okay? I'm an astronomer that knows, you know, the objects and those things, but what I don't know sometimes is some of the theory and some of the mythology, which people find fascinating. So Daryl is a wealth of information, and Daryl is going to get embarrassed again, but I call him the astronomer's astronomer. He's able to put it into words that I think make people feel involved and immersed in this stuff, and I love it. So thank you, Daryl, for that.
No worries.
So here we are. This is, as Daryl said, Auriga, the charioteer, and we have our telescope on Auriga, on Capella right now. And
Are you going to sync to it?
Yeah, that's what I'm doing right now. So you'll see the little plus sign goes zoop down here. There it goes. And so now when we actually center up, we'll see that we have in here we have Capella close to the center, right? So it's within that inner circle, and that's good. All right. So that said, what we're going to do now is go to one of the objects here in Auriga that is really interesting, And as we do this, we're doing this because as time goes on, we're going to find that there's other objects rising in the east that we're going to look at a little bit later that are really phenomenal. I do want to get to the Crab Nebula as well, Daryl, which I think is interesting.
Oh, yeah.
Hey, Sam S., how you doing? Nice to see you. Yeah, Bonnie, he does rock. She says, Daryl rocks. Yeah, he does. Yep. Yes, the red X, Marianne, was the centering reticle that I put up there. I meant that. I put that up there on purpose. I hope that's what you're saying. All right. So, now that that's up there, let's go check out some of the deeper views within Auriga. Okay. And we'll have some nebula music now. All right. We're going to come to this nebula here called the Flaming Star. We're going to go to the letter Y as well in a bit because down in there, there's another feature, a gorgeous feature that we're going to see called the Tadpoles. So we're going to move on now, and you'll see the plus sign show up here. This square represents our field of view, and it basically follows the center of the screen, not the reticle here. So if we center up, though, then we see what the field of view looks like. And if we zoom in, you'll notice it's on an angle, and it says that it is 1.5 degrees by 1 degree tall, basically. And that's what we're looking at right here. And at this angle that we're at, this would give us a really nice view of this particular object, but it'll be horizontally placed. So let's go see just how well our placement was. So we're going to come over here. First of all, for those that are just joining us, I am going to go through this just to give you just a little primer, what things are, what they are, and what they look like. Okay, this over here, this is our telescope control system. This is our view into the telescope computer. These are the views looking at the telescope. Okay, and this dummy is me. Okay, this of course is our main view, and this is our camera cluster over here. The most important values here are the exposure, in other words, how much time we're letting data fall on the sensor, and then this number here, the gain, how sensitive that sensor is that we're letting the light fall on, and that will determine a lot of our exposure. The gain of 250, it's a little bit high, but we're using that tonight because a gain of 250 is going to allow us to see fainter things faster. And because our telescope is so fast, we can see things very quickly. And let me just tell you this. This telescope we have right here, the one that you see right there, okay, right over my head, okay, this telescope is the only one on Earth that's been modified to be this fast. This is a Meade Instruments telescope, and there's no other Meade telescopes on the planet that have been modified like this. This is the only one. It's a prototype. And believe me, we're taking advantage of it. Now, let's do this. Let's look at our whole sky. We're going to do another solution here, solve. This is the previous solution. And let's get our new solution. And there it is, right in the middle, the Flaming Star Nebula. All right? So that's there. So what we'll do, I can actually see it now. We're going to come in here. We'll do a 25-second exposure, which is 25,000 milliseconds, as you see there. And then we're going to tell it to go. There we go. And while that's coming in, we're going to stack it. And this stack is going to allow us to see the first image that the telescope takes of this region, and then the second one will be stacked on top of it, and so on. So we do a few of those so you can see. So, And Marianne's been sending me messages. I better listen to them or I'll get in trouble. Oh yeah, there it is. Now you see, why is it blue? I'll tell you why. If you look over here, right over there on the right, you see these curves? This is the red curve. There's a green curve and a blue curve. Well, this white curve is the average. And the average shows that the red curve is kind of to the left, meaning we need more red in here. All right, so we have to color correct, and that's what I'm going to do right now. Those three curves now, red, green, and blue, are going to align under each other, and then the white curve will line up with them. Ready? Here we go. Do that. I click that button, and boom. Now they're aligned. And now, let's get rid of this extra brightening of the region right now, and just do this. Look at that. Look at that. That's beautiful. That's the Flaming Star Nebula. Flaming Star, because it looks like one. This is the star. You'll notice there's some blue stuff here. It looks blue. That's called Reflection Nebula, which I'll explain in a minute. And this red is ionized hydrogen gas. So there's a lot of things going on in this star-forming region that I think are really interesting. Yeah, Stephen, it's the only telescope on the Earth that has been modified for Meade. There's other telescopes that do this, that have this setup, but we're the only one on the planet that uses Meade Instrument Corporation's telescopes and modified those to do this. I don't know, I saw the magic potential here, and it really is magical. You know, Daryl and I have been astonished by what this can do. This is 25-second exposure, and look at everything you see. See all this very subtle detail. Now, we've stacked 5 images so far. That's right, it's the Hyperstar system made by Starizona down in Tucson. And they've been consulting with us and have done a fine job with us, helping us out. Yeah. So yeah, and just so people know, I mean, we've been adding capabilities to our system. One of them is we're using this now. We've upgraded the software to use something called color noise reduction. We always had this extra enhancer to the detail here, but we now have what's called a full width half maximum filter. And what this is it's a filter that actually looks at the size of the image, and if it falls within a range that you specify, then it'll accept the image and allow it to come in. If it doesn't fall in that range, if it's outside or too big, it won't come in, and that guarantees that we have perfect stars in our stacks. So far, every image we've done has been nearly perfect here. 1, 2, 3, 4, 5, all of them, all 8 images. If you look here, it says 8 images stacked, okay, and then 0 have been ignored. If we saw a red one here, which may happen as the wind kicks up here or there, then we would notice that we'd have one that was rejected over here. We don't have any yet. Let's zoom in a little, Daryl, see what we got here. Go back to the histogram. We've got 10 images that have been exposed here. Notice how the stars are nice. I got a little focus issue. And I'm going to refocus because I am using temperature compensation, but it looks like that temperature compensation coefficient I used is not accurate. So pardon me, guys, while I eliminate this, don't save it, and just do a focus run, which actually is kind of fun to watch. So let me just do that. So first things first, we actually take the stars out of focus and we allow them to be brought back into focus by our focusing algorithm. All right. So now we run in the, we went positive to over focus. Now we're gonna bring them back to perfect focus by coming back down. So it's like twisting the knob on your focuser and then twisting it back, all right? And then finding your way to the center point where it's perfectly focused. We'll see that perfect focus location show up as the lowest point in a curve that's being built over here. And up there you see 3 of 12 process. I set up 3 of 12. You could go, it could have been 25 or 50. It could have been any number. 12 has turned out to be the right number for most of what we do. These are sample stars, and we're finding now that it's 5.318 is the score based on the size of the image. Best was 4.794, now 4.8. Okay, and when we get to the center, that will pick the center point here, and it'll build a line through this, a line of best fit. These are discrete points, and it's going to build a line of best fit. The more points you have, the better the focus will be. I found that 12 is more than enough. So right about now, we should start seeing a line. There it is, right there. That's a line of best fit. And you'll notice that it was, it went down to like 4.71 or whatever it was. So now that we got that, I don't have to let it complete. It'll refine it slightly, but it's an outlier. So now we focus, and it twists the knob all the way to one side and then the other side, figuratively. All right, and so now when that comes back, you'll see that we have perfect focus here. We'll just wait for a sec. There we go. All right. So there we go. So it's done. And now this image will be perfectly focused when we take the picture. The stars were slightly out of focus, but we'll do 25,000 or 25 seconds. All right. So we come back in here to the live stack, and I'll show you something. Okay, we'll get rid of this. Our live stack got rid of the live stack. Never mind. I must have cleared it. Hey, Yasser, how you doing? I know. There's nobody else doing this. There's no one. There's people that do astronomy, yes, and they even show their telescopes and they broadcast it. But there's no one doing this. There's no one. As an astronomer with Daryl, okay, there's no one sitting here showing you objects and then telling you all about them, their importance to us and everything. You know, no one's doing that. It's just like, wow. I mean, are we really doing something that is that hard to do? I mean, maybe. You know, I mean, I am doing it from 2,500 miles away. And we did, you know, I do have Marianne Marianne Robb and Tara that's actually are helping us do this. And so I guess without them, this would never have happened. All right, let me color correct. There we go. Now you see the grain in here? That grain is because we've only got 3 stacked. As we stack more, the data comes to the top, and all that random noise, which is making this grain, is getting averaged out. And before long, this is going to look like a beautiful, smooth image. In fact, it'll happen before you realize it. You know, let me, I can simulate it too. If I come over here, it'll make the image a little dimmer for the beginning here. But watch, as I pull this, I come in here and pull it down. Okay, you'll see. See how it looks a little smoother, you know? But we want this to be able to show us some detail. Now this white curve is our average of the red, green, and blue curves. As we go, sometimes we have to correct along the way, and minor corrections are made. And what I'll do is, this is our black level, and as I move that black level over, we get to the peak of the curve, and that should give us, when we get to the top here, that'll give us the blackest view of the nebula without ruining data. Keep going, on the other hand, and now watch. Now we start losing the nebula, okay, because we're over that white peak. We want to stay ideally just to the left of that peak, and that will give us the finest detail. And if we tell it to do an auto, it's called an auto stretch, it wants to be out a little further. Now we're up to 6, and you'll note these blue regions coming in, which I'll discuss shortly. Thank you, Stephen A., for your compliments, and thank you, Cindy Murphy, for your compliments as well.
Mark, refresh my memory, please.
Sure.
What is the native F ratio of the telescope? F8 or F10?
I think it's F8,
Okay.
and I went down to F2.
Yeah, that's what's allowing Mark to bring images to you so quickly. F2 versus F8 or F10 it's the focal ratio of the telescope or the system, but photographically it's just like any camera lens. If you're shooting at F2, you can get the exposure a lot quicker than if you shoot it at F8 or F10 or F22, whatever.
Yeah.
With most camera lenses. What he's grabbing with a 25-second exposure would take many minutes or hours to capture at a higher F ratio. And that's what Hyperstar is doing for us here.
Yeah. I admit, the Tucson folks talked me into that, and I think it was worth every bit, you know?
Yeah. The trade-off is it's a low-power, wide-field view, which is great for deep sky objects, but conversely, it's not great for looking at planets, because planets are very small.
Right.
So we can catch big gas clouds, but planets kind of suffer under the Hyperstar system. They're small, they don't show much detail. But hey, deep sky objects are where it's at.
True. We do have a second telescope that's going to be going in. And that telescope is going to have what's called a higher focal length, meaning we're going to be able to see close up. So, as an example, if we looked at this region with the next telescope, this is our field of view. The next telescope's field of view was probably going to be like this. Okay. And as you can see, that means that if we zoom in on that we're going to basically see very little nebula and very little structure. We'd have to do lots of mosaics of the whole thing, which is great. We love mosaics. But who wants to sit through that? I mean, I get impatient too, because I want you to have the best bang for your buck, which is zero here. You know, there's no charge. Unless you want to support us on the Patreon, which we need. Okay. But this is something else. Hey, James Hyatt. Welcome. Good to see you. Hey, Radio's with us. That's our friend Ronald. Ronald is a real good friend of Sky Through a Livestream. One of our amazing supporters. Ronald, we are going to be previewing a property in the coming month here, I think, out there to find a site. Our previous site that we had selected turned out to not be the best site, as we noticed some construction and some things going in. So we took a step back and decided we're going to do this right. We're also looking, in a way, moving forward, if we get enough people helping us out in the Patreon, we're going to put a telescope in the southern hemisphere eventually, and that's something else that I want to do, because I don't need sleep. When it's daytime in the United States, it's nighttime in Australia, you know. So the other thing we're doing, in a very, very serious thread here that we're doing, is we're building a portable observatory that we're going to truck around the country and bring to college campuses, schools, and broadcast live streams, but also do it live for a studio audience. And that is something that we really, really want to do. I've designed a trailered telescope that it'll have auto leveling legs like these RVs do, and they'll level the telescope perfectly. And then all we have to do is align it, which takes no time at all. And then we'll be able to do everything we're doing now. And the setup time for this, I open up, and the setup time's about 25 minutes to get it ready. The setup time for the remote observatory, the mobile observatory, is going to be about 25 minutes, about the same. It won't be a big difference at all. So that's where we're going, you know. Hey there, Vince Giglio, how you doing? Vince Giglio says, impatience and I think he means astrophotography don't go together. You're absolutely right. They don't. Okay, we got 20 shots here. Notice that modeling is gone. Look at this. Now we have some leeway to start doing some processing, and I'm going to do that right here. I'm also going to try to punch it up a little bit more, like this. Let's see if this helps us out. Yeah. How about this? Oh yeah, look at that. That's just beautiful. This is known as the Flaming Star Nebula. The Flaming Star. And there it is. Okay. I will bring that back in a little bit. In fact, why not? Why don't we do this? Why don't we, while this is coming in, let's do this. Let me actually get rid of our telescope here and just bring us to a full screen so you can watch this thing coming in. This is just a beautiful nebula. Look at that. Now let's talk about this. Okay, if you look over here, okay, you see this blue stuff right here? That blue stuff is called Reflection Nebula. Beautiful example of it's right here, this arc. See that beautiful arc? Now what's happening here is neat. The star is very hot, okay, but it's also hot enough. It's hot enough to ionize the hydrogen, which looks red. Okay, when you kick the electron off the hydrogen atom, when it drops back in, it gives off a photon of light. That photon is red. In this particular case, it's the predominant one. There's more, but this is the predominant color. And the blue, on the other hand, is not coming from such a reaction. The blue is coming from the fact that you also see dust through here. You see these dark areas. That's dust, interstellar dust. And if you saw my Facebook post, as I mentioned earlier, it talks about the interstellar dust in the universe and what it means to us and for life on the Earth. So this dust is actually playing a role in making this blue color. How is that possible? It's not being ionized. It doesn't do that. But the starlight is made up of red, orange, yellow, blue, green, indigo, and violet light. That's Roy G. Biv, by the way. And the blue light is particularly interesting to these tiny particles of dust that we see in this nebula. And the blue light is actually scattered in all directions by that dust particles. So in many cases, we'll see very subtle and very beautiful gossamer strands of blue that we see, like this and that and here. And that's areas where the dust is dense, and there's enough dust to actually scatter and be seen over the brightness of the red scattering, the red ionization nebula. So it's very, very complex the way it all works. But that's actually, if you said that, you'd get an A on an astronomy test, okay? Because that's true. It's scattered light, not technically reflected light. And it's known as Rayleigh scattering. And you might have seen that before. Every time you see daytime. Notice anything? That blue is the same color as your blue sky. And the reason is because these particles are scattering the blue light just like the molecules in our atmosphere scatter the sun's blue light in its spectrum. So that's why we have blue sky. That's why we have blue nebulae. There you go. So hopefully that gives you a little bit of an explanation for the different colors and what we see. Let's zoom in a little here. Look at that.
Looks more like the Smoking Star Nebula.
It does, doesn't it? It's really pretty. And our stars look nice. I can still bring up our stacking and actually just take me to the peak and darken it just enough to show the detail a little better. And we can actually play with this slider. This is a mid-level slider. It has to do with the brights of the colors, and by pulling it down, we'll see that we actually are finding ourselves seeing more detail of some things and less detail of others. So, but it looks very smooth right now. See that? How nice it looks. It only gets better. Now we've got 31 frames stacked here, and we will be able to deliver this image just like you see it to you, and it'll be free. How do you get it? To test. That's right, skytourlive.org. And by the way, we have the Flaming Star on a number of our products over at SkyTour shop up here, so head up there and check it out. It's on Etsy. Yurtza Morales says, wow, hermoso, beautiful. Sí, es la verdad. Es la verdad. Gracias. So this is really pretty. It's a beautiful nebula, a beautiful location. And now we're just at 33 images, and I think that's good. And we're going to change our name up here to Flaming Star. Okay, nebula. And it's a mission nebula and a reflection nebula. I know I just told you we say scattering, right, when it's blue. But effectively, in astronomy, when we see a blue nebula, we call it a reflection nebula. And yes, the process by which the light's coming to you is through scattering. But rather than explain what scattering is every time they talk about it, we call it a reflection nebula. All right? It's an EN, a mission nebula, and a reflection nebula. So we can come back, dock up our thing here, bring back the telescope here. Okay, there we are. And now what we'll do is we'll save it. Just like we see, this is 36 exposures. All right. And you came along for the ride. This is the universe live in real time. Excuse me. I've been talking so much that my voice is going, so I'm sorry about that. And I don't mean tonight. I mean I've been talking a lot. Radio shows, things like that. Speaking of radio shows, if you want to hear Daryl and I talking about astronomy, Sunday nights from 6 to 8 p.m. on KGRA, we have a radio show that's heard all over the world. and you can join us. It's a 2-hour foray into astronomy, the latest things, the latest discoveries. And Daryl takes us on what we call a deep dive, where he shows you the night sky and takes us on a tour of what's to come. And it's really, really wonderful to do that. And he is damn good at it. And it complements the astronomy we do. It's really nice. That's astronomy as well. Visual astronomy, right?
Sure.
Okay. Save this one more time. And save exactly as seen. James Dugan is in Australia. Speaking of Australia, Happy New Year to you, James. Welcome to the show again. Good to see you as always. Okay. James, I may have asked you this, but do you have any idea of relationships we can cultivate down in Australia to be able to get a telescope down there? I'd have to come down and do it, and I certainly would. If I twist my arm, I'll go to Australia. It would probably have to be for about 3 weeks or more to get used to the time change and then be able to work and have access to materials and stuff. Okay. There we go. All right. So I'm going to back out of this view now. This is at 56% of our 100% sensor. Okay. And then what we're going to do is go to that next thing I mentioned to you. So that was a little too much. What's that?
The crab?
No, the tadpoles while we're here.
Oh.
Yeah, they're right below this. Right here. Eric is here with Eric's Automotive Diagnostics and Repair. How you doing? Okay, we'll go right here. That cluster, we're actually gonna center the telescope here. So I'm not gonna go to a specific object. We're gonna center it in that square. So our telescope's gonna move slightly. You'll see it in the telescope view here. There it goes. It's moving ever so slightly, and then we go into the middle here, where we are going to be able to image. That's the letter Y cluster right now that we're on, which is right here. And you can see why it's called the letter Y. And the tadpoles that we're looking at are going to be right about here, if I recall. And these are really pretty. We're going to make these a 25-second exposure. And as Daryl said, in 25 seconds, we can capture what would take minutes or even hours sometimes. And that's something that we are really, really pleased with this telescope about. Daisy and Zoe, hello. Nice to see you. That's everything that's in this region for the flaming star. Okay. And I'm going to clear this. And then knock down this other area here. And now we should see our first shot of the tadpoles. Now you say, well, that doesn't look too exciting. Give it a moment. Give it a moment. We're looking right here. All right. And I will do a color adjustment here. And you'll see the nebula begin to jump out at you just a little bit. Okay.
I see them already. They're not very distinct yet, but
not yet, but they will be.
That'll come.
Yep. As you see now, just with a little color correction, they jump right out at you. Remember what I told you about the curves? You can see that our white curve is the average, and when you color correct, the average curve moves appropriately. And so we can bring this peak just to the left of the top, and that'll bring out more detail. Look at that. Look at all the extra detail just showed up. Okay. Yep. Daisy and Zoe, thank you for the well wishes to us. Nice. So, very quickly, we can just zoom in just to see what's coming. Right. These are the tadpoles we're looking at right here. Now, we only have 4 images stacked. And some of the noise is still there. You can clearly see there's still some noise there. Okay. But it's not bad. See that? So now you can see them. And very clearly here. So as we back out, we'll wait for more frames to come in. We've got 5 selected. Now you notice I'm looking this way as well. Okay, this is a giant curved screen in front of me. The left side is the observatory feed, and the right side is all the other stuff with me on it, and my ability to point stuff out is here. Okay, when we talk about tadpoles, we're talking about this guy right here and this guy right here. Okay, so those are the 2 tadpoles we're talking about, right? Now, while we're doing this, we might as well come over and do a solution on this. We'll do our, this is called a plate solve, where you calculate, you let the telescope figure out exactly where it's pointing. And we did. And it sees the open cluster, all right, which is the letter Y cluster right down here, all right? And I see 410 Nebula that's here as well, which is the Tadpoles Nebula. This whole thing. So there's our tadpoles. Now, what are the tadpoles? Okay. Interesting region of space. Okay, the Y cluster, the letter Y cluster, this right here, is, and don't struggle to try and find the Y, because it can be oriented any which way. Okay, but when a cluster forms, the stars that form in the cluster have an extremely huge effect on the gas around them and the dark nebula and dark dust around them. Dark dust is harder to move around. The gas, on the other hand, is not. The gas is very light. A hydrogen atom in deep space, is a proton and an electron. Okay? And when they ionize, it's just a proton. That's extremely light compared to a conglomeration of hundreds of thousands of atoms. Even more, making up dust particles, millions of atoms. So, dust is harder to move, so the star's radiation can push gas around easier than dust, and it'll shape the dust. And we're seeing that here. It's shaping these dust spires in the same way, because the cluster is here, and the radiation is pushing this way, and it's pushing all that gas away as it ionizes it. So it's pretty interesting how that works. Okay. Eric says, would you rather have an hour with Hubble or JWST if you had only those 2 instruments? James Webb, hands down. How about you, Daryl?
I don't know. I'd probably go with Hubble.
I think the James Webb would, for me, but that's okay. James Webb has the ability to see inside these dark clouds, and inside the dark clouds, okay, and Hubble can do it to some extent, because James Webb sees infrared, okay, and the infrared energy that the Hubble sees is only a fraction of what the James Webb can see. So if the Hubble sees the infrared to the width of my finger, okay, here or that down below in the lower left, James Webb is way out here. It's actually, several inches, actually a foot and a half more to the next deeper infrared shot. So deeper into the infrared. So James Webb specifically is for looking at galaxies that are so old that they're so far away that their light is entirely shifted into the red end of the spectrum through what's called redshift. As things move away from you, their data shifts into the red. And as Edwin Hubble found out in 1929 or so,
23, I believe.
23, was that when he came up with the Hubble constant?
Yeah. That's when he was working on it, anyway.
Okay. As the galaxies move away from us, they actually are moving faster and faster away from us. And that speed of recession, it was called, moving further away faster, led to a parameter called the redshift. And the redshift was something that was very, very important because that gave us distances to galaxies and allowed us to learn a lot about cosmology, the fabric of the universe. Okay, so we have 17 images shot here. And we're starting to get detail within the tadpoles now. You see that? That's really pretty. We're going to go right to the peak here, darken up a little. Look at that. Wow. You can see those distinct spires that are trailing behind. Let's back out a little. Look at the overall picture here. See that?
1924.
Okay. Now the Flaming Star Nebula that we just looked at, see this red? That's part of it. It's north out of this shot. Yeah, our views just get better and better with our technology, and as Daisy and Zoe say, the James Webb is 100 times more powerful than Hubble, and that is just crazy. Yeah. In general, Ronald, as Daryl just told you, red is ionized hydrogen and green will be ionized oxygen. Now, you might say, why hydrogen and oxygen? What the heck? Why? Well, it has to do with what are called the fundamental amounts in the universe. And when we look at the fundamental abundances, as they're called, hydrogen is the highest abundance. So we're going to see lots and lots of red nebula in the universe. And if we look at oxygen, well, next to hydrogen, the next most abundant is helium, right? And after that, the next most abundant element in the universe is oxygen. And after that, carbon. So that's why it stands to life that we see a lot of these dark clouds, which have a lot of carbon molecules in them, and carbon debris from supernovae that have blown up in times past. So this is incredible, all right? So I think that it's very important to understand that this dark nebula here, these are the things that spawn life. These nebulae spawn stars, and for a period of time, we'll see these stars in here that are very bright and hot. But eventually they evolve. And when they die, they may go supernova, leaving behind black clouds of there's all kinds of stuff in there. You've got iron in there. You've got all the elements that supernovae make, which are quite a lot in the periodic table. It's pretty cool. Cosmic Ray, when I was talking about interaction, I wasn't saying that the tadpoles and the flaming star interact. I'm saying that if you keep going up here, you'll see the flaming star, and the flaming star is much closer to us. So, but how far back this hydrogen goes? Well, we know that there are arcs of hydrogen in the galaxy that are tens of thousands of light years long, you know, and so it's possible that they're linked together. I don't know that they are, but it comes from a very a region of high abundance of this stuff. James Dugan, that's right. Yeah, folks, make sure you're on 1080p so you get the highest resolution here, will you? Thank you, James. I don't say that enough. Hey, Marco. Hey, Science Bob. Science Bob says he loves this nebula. It's one of my favorites, too. A lot going on in here. Okay, we're at 28, and we'll stop here in just a couple of shots and move on. Because I want to take you to a supernova remnant. Because it should just be visible now. Look at that. That's pretty, Daryl.
It is.
Let's see where it wants to put these. Yeah, that's what I thought. Yeah. To pull out the most detail, you could go to the left, but then, you know, we brighten it up too much. And that brighten isn't sky glow because it's dark out there. It's just, it's adding artificial brightening to the scene, just like when you add brightness in your imagery. It's adding brightness that isn't there. So you have to play with these values. But look how beautiful this looks. Let's zoom out. Just a little bit.
Moon is up at 11 local time tonight,
Yeah.
by the way.
That's 2 hours from now. Arizona time. Look at that. Excuse me. Yeah, that's pretty. Go back. All right. Okay, 32. We're good. Let's change the name. We'll call it Tadpoles because that's what I've been calling it. So we'll save it. Save it exactly as seen. I'm glad we got this night because it was not looking good initially. And Daryl's showing you the link where the images are dropped, so you can go check out tonight's images. Make sure you visit skytourlive.org though, so you can read the instructions as to how to navigate the directories to go find them. It's not pretty yet. We're still working on that. Can't do everything at once. All right. So that's good. So let's bring up our annotations now. And once we get our annotations, let's save the image with annotations. Okay, so that's saved now. Okay. And then this nebula, we'll save it. Notice the number of objects are shown here. That's the objects in the view, and not all of them are listed at one time. I mean, they're there, right? But we're not listing all of them. We'll do that and save it because that'll be yellow. It'll look brighter. In case you want to know. Okay. All right. So this is really pretty. I'm glad we did this one. Now we'll get ready to go to our next one here.
Now the crab.
Yep. Now the crab. I didn't let it come up. I tried it earlier and it was still below the observatory wall. So I had to let it come up, which I think we've done. We also have California down in Perseus, right? So we can do that. Yeah, we're good here. Crab is right here. Ta-da! We're very close to it, actually. Off to the crab. Now, the Crab Nebula is a supernova that occurred, a star that exploded, in 1054 AD. And Chinese saw it and documented a new star in the sky. And it was visible during the day. And that's what the Crab Nebula was. Excuse me.
Mark, you're muted.
Curtis Horn, you were right. Thank you. So the Crab Nebula, then, is a few thousand light years away. And it's a supernova. You'll notice right away when you look at it that there's filaments here. You can see them right here. These filaments. There's lots of filaments. And we'll zoom in on those in just a minute. But what are those filaments? Well, when the Crab Nebula exploded, it was a star. And it blew up. It blew its guts out into space. And that explosion scattered debris to the interstellar medium. And if you imagine, there's a lot of charged particles in that location. So those charged particles could very well be responsible for some of the tendrils we see here in the Crab Nebula. We've got 5 shots here. Let's zoom in a little so you can see these better, because there's something else in here you got to see as well. Okay, here we go. This is one of the nicest shots there. Look at this. Wow. That's beautiful. That's really pretty. I'm just zoomed in a little too much there, but that's okay.
You see the
Now,
central neutron star.
that's right. Right there, guys. That star right there, okay, that you see in the middle, that star is a star known as a pulsar inside the red square. Now that pulsar, that's, as Daryl just mentioned, a neutron star. Okay, not a white dwarf, but a neutron star. It's the next level up. It's for more massive stars. When they go supernova, they're going to become either a neutron star that's just a neutron star, or a neutron star with hot spots that are spinning rapidly and flashing us every time they turn around. That becomes something called a pulsar. Or they can just become a neutron star that has an extremely high magnetic field called a magnetar. That would rip you apart if you got within a couple light years of it. But the thing is, this particular neutron star is a pulsar. It has a lighthouse beacon of hot material that is emanating off of it, hot radiation. And it's spinning very fast. Now, how big are these neutron stars? The neutron stars are small. They're the size of a city. They're the size of Manhattan Island, basically. And if you can imagine a star, the diameter of Manhattan Island over your head, massive. Now imagine that star spinning 33 times per second. And that's what you got here. That neutron star,
thousands of light years away, and you can still see it, even though it's only as big as Manhattan Island.
that's exactly right.
Means it's extremely bright.
That's right. And that energy is enough to ionize this material that's already light years away. This debris cloud is light years away from that central star, or the remains of that star. Now, the neutron star is very hot. If we worked it, we'd probably see that neutron star was a very, very blue, hot blue. The hottest colors in the universe are blue. The next hottest colors are white, and then yellow, and then orange, and then red. Okay? Now, if you notice, okay, let's do a color correction here. And there we go. And now let's actually enhance the colors a little bit. Okay. Because now you can see, as Ronald said earlier, this green tendril here. Oxygen. And red. This is hydrogen. So there is oxygen and hydrogen. Again, the two of the most common elements in the entire universe are visible here. Okay. So this is what is par for the course with supernovae. We get a lot of green and we get a lot of red. For those that have followed us with the Veil Nebula in Cygnus, we will often see beautiful green filaments with red punctuated filaments as well. Hydrogen and oxygen, the first and third most abundant elements in the entire universe. It stands to reason we'd see them when it's done like this. And as Daryl mentions in the chat, when the neutron star is formed, it tries to collapse, but it can't collapse any further. Now, let's look at a white dwarf. A white dwarf is a star about the size of the sun. When the sun goes to a red giant someday, it'll collapse down, and its remaining core will not be able to collapse further than just being a carbon and oxygen dwarf surface. And the electrons and the protons in the atoms will be loose from each other because it's so hot. And the electrons will be squeezed. and they can't be squeezed any further because there's not enough mass, not enough gravitational contraction to squeeze them further. And that's called electron degeneracy pressure. Imagine a checkerboard, and in each square you put a single electron. You can only fill the number of squares you have on that board. You can't put 2 in one square. All right. Similarly, with a neutron star, the more mass allows you to literally double up the number of squares on that same size checkerboard. And so now you can add more things into those squares, and what they are is neutrons. And you squeeze the neutrons together, and those neutrons can't be squeezed any further. They push back, and that's called neutron degeneracy pressure. That's what holds the star together. And it's also the thing that makes sure that we get a neutron star and not the next thing that happens after that, a black hole. If we had more mass, then even the neutron star can collapse further and go past and through that neutron degeneracy pressure. That final state is the black hole. And we see that galaxies in many cases have supermassive black holes at their center. We know you can have micro black holes through a special physics loophole, and we know that you can have stellar-sized black holes. Now, many people will say, well, what if you put a black hole where the sun is? What happens? I know Daryl knows the answer, but if we put a black hole where the sun is, tell me what happens.
Are you asking me?
No, I want the people in attendance.
Oh.
Let's suppose you put I know, Daryl, I know you know. If you put a black hole where the sun is, what would happen to the planets and everything else?
Is it the same mass as the sun?
Yeah. Let's assume it's the same mass as the sun.
Nothing would happen.
Why are you answering? I told you it's a chat thing.
Oh.
Yes, nothing would happen. You know, because the sun would just be dark, but if it has the same amount of gravity, then the planets would continue to orbit. Now, the sun is too low in mass to become a black hole. It never will. It's too low in mass to become a neutron star. It's not too low in mass to become a white dwarf. Now, if you want to see white dwarfs, we have to look at planetary nebulae, and then you look in their centers, and there's a hot blue star in there. That's a white dwarf. Those are about the size of the planet Earth. But still, from thousands of light years away, you can still see them because they're very, very hot. And they can ionize the nebulae around them as well. The Helix Nebula is a well-known example. The Dumbbell Nebula, another. The Ring Nebula, possibly another. Although, I have seen some research that indicates that the Ring Nebula star is actually potentially a Wolf-Rayet star, which I thought was pretty cool. So, pretty cool. Okay, so we got 24 of these, and we're going to check it out. Look at all those beautiful filaments. Yeah, we got it labeled already. Okay, good. All right, 25. We'll save. And save it exactly as seen. And then we'll just, for purposes of continuing, we'll do our plate solve for the region and see if it puts it here. Okay, it's doing the plate solve. Is going to tell us that that's the M1, Messier 1, the Crab Nebula. Supernova remnant, magnitude 8.4. Neato. And we'll save it with the annotations. All right. Daryl, thank you for putting up the image locations.
No worries.
Okay, so now you know about supernovae. Now the thing about this is it looks like it's not moving, but it's moving at many kilometers per second. It's moving outward. Because it's so far away, it takes a long time to notice this. And I think that it would behoove us to find that video of the 100 years of observation of the Crab Nebula. And you can actually watch it expand over 100 years of observation. Okay, Mind Remote 7, who actually won a pair of binoculars from us last stream. Congratulations, Mind Remote. So Mind Remote she says, a black hole the size of the sun, and Daryl's answered it too, and the same mass would not collapse the planets into it. No, because all that governs how the planets orbit the sun is the gravity of the sun. And if the gravity of the sun doesn't change, but we swap the sun for a black hole that's the sun size, then then nothing would happen except we would all freeze. All right. Most likely Mercury, Venus, and the Earth would get fried by the radiation that black holes give off, because black holes are always losing mass and radiating away. They're actually evaporating, in fact. But it's so slow that they effectively last the life of the universe in stellar-sized black holes. Yeah, cool. Mind Remote, let us know what you think of the binoculars that you won from us a couple nights ago, or a few nights, actually about a week ago, huh? Okay, we'll save this one more time. And save it exactly as seen. Correct, Vince Giglio. Gravity depends on mass. Two equal masses will have the same gravity. That is a correct statement. Okay, we're going to get out of the Crab Nebula now and move on to something else that really tickles our fancy. So let's do that. Okay. Let me see if this live stack is still here. It looks like it's going to be auto removed. Let me try. If I do this, will it auto remove it? No. Okay, here's another feature we can do is we can do this. We can actually show you the negative, and it shows you these beautiful filaments very, very clearly. So that is another feature that we now use a lot, is that negative feature to actually show faint detail that we might otherwise miss. So if we come back here, okay, and we do this, you might miss that there's filaments up in here. Okay, go negative and you can see that there are filament structures up in here that are very faint. See that? So this is another feature. In fact, when I was getting my degree in astronomy, all I ever saw were negatives. I never actually looked at positive images like this, okay, that I'm about to show. We only looked at the negative images because we were studying faint structure, and the negative was actually the best way to show it. Okay, so we'll come out of here now. And we're gonna come back to our 1 second here. Okay. I'll get rid of the stack here. I obviously did get rid of it. I gotta redock it. Okay. Then I can get rid of it. Okay. There we go. Now, there we are. Okay, so let's zoom back out. We'll go to 25%. Good. All right, so now where we are is we're actually able to get to Gemini, which is right down here. And we're going to take a look at another cluster, which is really fascinating. It's called Messier 35. Excuse me. And Messier 35 is a brilliant cluster of lots of beautiful stars. And what's interesting about Messier 35 is it's got a companion cluster right here. That cluster is very much further away, and so you'll notice that the color is redder because we're getting something called interstellar reddening. The farther away it is, the redder it becomes. So let's just pop it eastward just a little bit here. And once we do that, we'll wait for the obligatory 12 to 14 seconds to get our guide star. And then we'll take a picture of this amazing jewel box of stars right here. Eric, I don't know if you're answering that now, Daryl, but I'm just going to answer. Oh, okay, I'll let you answer. Yeah, well, what he's saying there is pretty straightforward and correct. But no astronomer, astrophysicist, or cosmologist believes that the center of a black hole is an infinitely small point. No one does. But for mathematical convention, we make the assumption that the gravitational force of a black hole works at the very center. We do that with the Earth as well. Between the Earth and Moon, the equation for the gravitational pull between Earth and Moon is well known. It's called GMM over R squared. 1m is the mass of the Earth, 1m is the mass of the Moon. G is called the gravitational constant. And the radius between them, measured from the center of each body. So it's for mathematical convention, as Daryl pointed out. And that's why this has people confused sometimes, and I don't blame you for being confused. Okay, we're gonna do 25 seconds. No, actually 20 seconds here.
Mark, would you excuse me a moment, please?
Sure.
Right back.
Okay. 20 seconds, and we're going to stack this. This is Messier 35 in Gemini. And that is the Crab Nebula remaining. We're going to clear that now from the last photo. And when this comes in, we will be able to do our solution and show you what exactly we're looking at. Look at that. And there's the color difference I promised. So let's color correct first. Okay, now we will just adjust. And there you go. Look at that beautiful jewel box. What I'm going to do is actually, as I mentioned before, we're going to come up to our average curve here. And we're going to bring it up to just left of the top to really darken up our background. Look at that. Mind remote 7 acids are a concept of degeneracy pressure for black holes. Now, see, all things fall apart when we go to black holes. We're okay with neutron stars that become pulsars, that become magnetars. You know, a very, very high, massive, powerful neutron stars. But when you do the black holes, a whole different world opens up. because now you're also messing with the fabric of space-time in a way that is just not normal. And so, the effects on time are extremely more pronounced for a black hole or for a neutron star in general. So we have to consider that too. So it's not the same. Light Up says, hold my beer and send me in the black hole. Yeah, no, because then we'll never see you again and I'll get your beer. Okay? Now, another concept I think is really important to understand. Black holes, they suck, right? I mean, that's the joke, right? But think about this. Black holes are interesting for the following reason. They say that they're so powerful that not even light can escape it. And that gives you the feeling that light gets sucked into a black hole. And this is the part that's gonna blow your brain up. It doesn't get sucked into a black hole. Wait a minute, Mark, you can't say that. Yeah, I can. See, it's not that light is getting sucked into a black hole. Light has no mass. Yes, if you want to talk about a relativistic mass, that's a whole different thing altogether. But light has no mass. A photon of light has no mass. So what's actually happening? Why can't light escape a black hole? Because a black hole isn't warping light. It's warping the path that light takes. Get that? The path that light takes. So a black hole warps space very deeply. So a proton a photon of light, an energy bundle of light, it's constrained to follow the curvature of space. So as it follows the curve, if the curve is really deeply curved, then the black hole can keep the photon from ever getting out of its confines after a certain point. That certain point has a name. That certain point's called, and many of you know it right now and you're thinking of it, the event horizon. So, the event horizon is the point of no return for all things. And it defines where light can no longer escape as well. Because space is so deeply curved, light is just following the curve. You think of light, you think of photons as a car on hilly terrain. Okay? As the car is moving along hilly terrain, it's constrained to follow the road. So it goes down, it goes up, it goes down, it goes up. And so space is the road, and the photon is the car. You bend space, the photon goes around the curve too. See? And that's the nature. It's a two-step process. Light can't escape a black hole, but not because it has mass, but because space itself is so deeply curved that light cannot get out of that black hole's gravity well. Okay, that space within the black hole, again defined by the event horizon. The event horizon is that point beyond which light can't even escape because of the curvature. That's the definition of the black hole. So, anyway, let's actually do a plate solve for this location and get the names. That's the previous thing we looked at. It's taking a photo and it's doing the search now, and it will tell us what these two clusters are undoubtedly. Yeah, Mesher 35 here, and this is NGC 2158. Okay, and if you look up 2158 versus 2168, you'll see the distance to this versus the distance of that. That's further away. This is closer. Okay, so there we go. I'm going to save this with the notations, and that way we're done with that. I don't have to do it again. Okay. So if you're enjoying this, please smash the like button. Please let us know you like it. And, if you feel like supporting us, man, well, we appreciate that. We need it. You can join our Patreon. If you go to our Patreon page, also found up here at skytourlive.org, you'll be able to determine if there's a tier for you to join us. And by joining some of our successive tiers in the Patreon, you'll get the finished, highly processed images that will take a couple hours to work on, and we'll deliver them to you. You'll get you get a link to them, and you can just download them. They are stunning. You can enlarge those, and we've actually enlarged some big enough to put on walls. Okay, it's really incredible. Oh, hey, Wild! I didn't say hi. I apologize. Is that Wild Ike? Is that what that is? Wild VK. Okay, VKE. So look at the difference in colors here. Isn't that crazy? I think Daryl's back with us now.
Yes. Yes.
So let's zoom in on this cluster here.
And it's not just that space is curved, space-time is curved.
Yeah, I was mentioning how the concept of time is a whole nother bailiwick within the black hole framework. Yeah. I see lots of hearts. Thank you, guys. Give us a thumbs up on the video too, because that helps our analytics. So if you look at Measure 35 here, you can see it's mostly these younger hot stars. I have to check to see if this red star is actually part of it. I'm not sure. It's possible, but I'm not sure. Because we have red stars here and here, and those are probably red supergiants. I know the question was before, will the sun become a red giant? Yes, it will. We're about halfway through our lifespan for the sun. And when the sun runs out of hydrogen, a number of things happen in fairly short order. The core of the sun begins to contract, and as it contracts, a lot more heat is thrown outward, and that will it will increase the size of the sun immeasurably, and that size will be what's called a red giant. And as the star gets bigger and bigger and bigger, the white color of the sun, which is white, by the way, not yellow. Okay, it's yellowed by our atmosphere. The white color of the sun will grow more red, because the farther away you get from that hot surface we see now, as that surface expands, then it's farther from the hot radiant energy coming from the core. And the intensity drops off as the square of the distance from the center. And so the color change will occur. The temperature will get lower. And temperature determines the color. As the temperature drops from, say, 8,000 Kelvin to 3,000 Kelvin, the sun will go from white to red. But it'll be much bigger. So the sun will become a red giant someday. And after that, it's just going to shrink down to a white dwarf. It's not going to get beyond that. Okay, we got 27 shots here. And I think 28 is enough. But look at this. Isn't this beautiful? What a jewel box.
Michael
Wow, that's
Hedrick has a question of you.
Okay, let me first do this here. We're going to call it Measure 35. Open cluster. Do you want yes. Okay. All right, we'll just save it now. Okay. Yeah, it'll be fixed. And save exactly as seen. All right. Cool. All right, Mike, what do you got? What's he say? Okay. How big of a telescope would one need to have to actually see this detail without stacking with your eye? 30 or 50 inch? No, this cluster here, you could see with some of the smallest telescopes. It's beautiful. This one might not be resolved into stars. It might look like a cloudy thing in some of the telescopes that are a little bit bigger, like a 6-inch or an 8-inch. But when you get to like a 14-inch telescope or greater, this may be resolved. Daryl, why don't you weigh in on that too? Because telescopes are and engineering of lens systems is more your thing anyway.
It depends on what you really want, Michael. M35 there on the left, it would easily resolve in any amateur telescope, I dare say, or well, say 8 inches or above. The cluster on the right, the smaller one, as Mark said, you kind of cross a threshold at about 13 or 14 inches where aperture, where all of a sudden everything changes, and it's like you're looking at it with whole new eyes. I dare say a 14-inch would show you that smaller cluster, much as
kind of
you
like
see
this
it in the image.
Maybe kind of like this with some of the smaller telescopes. This might look cloudy to you, you know. Now, this is a rough simulation at best, but as we move forward, okay, this cluster would look like that. You wouldn't see any hint of it in like a 6-inch telescope. Okay, you'd see this one here, okay, but you wouldn't see the small one. But as you get further in, more aperture, then you might start to see hints of what's here.
And you can look at it this way. Messier saw M35. He did not see that smaller cluster, or he would have put it on his list. Now, actually, Messier didn't necessarily discover M35. There were several astronomers who contributed to the Messier catalog: Pierre Michane, William Herschel, and others. But if Messier saw M35, he only had like a 4-inch diameter telescope. And he never saw that smaller cluster, or he would have included it on the list.
Right.
The largest telescope I ever got to look through was a 41-inch Dobsonian back in the late 90s. Up in
He
the
told me
dark
about
skies
that.
in the mountains
Yeah.
here. I got to see the Whirlpool galaxy in it, and through a 41-inch telescope, well, the live image of Messier 51, the Whirlpool, looked like a very nice photograph. There was so much
Wow.
detail to it.
That's beautiful. We're moving to a nebula called the Jellyfish Nebula. This is a star called Propus, and the nebula is here. I'm going to just move us over and give us room, because this one is a really, really beautiful nebula as well. Again, hydrogen gas. Let me just do this. I think that's going to be good. Maybe just bring Propus up a little bit. So dump down south a tad. All right. Now what we'll do is there's a nebula in here. Okay? And we're going to bring it out. So if you look at a telescope and you see this, what else is there that's in here? Well, that's the secret. You don't know until you look, and that's what we're going to do now. Is we're going to go digging in to this location. We're still searching. We haven't actually retained a guide star yet, but that's okay, because we have our full width half maximum, and if we don't have a good guide star, we won't get an image. So we'll just let that go for a moment. While we're waiting, I'll give my voice a rest. So if you want to mention some things, go for it there. Oh, there it is.
What kind of things?
Oh, whatever. You know, if you wanted to mention anything, if you wanted to talk about the Jellyfish Nebula or something.
I don't know
Look at
much
that.
about the Jellyfish Nebula. I've seen it before. I've seen pictures of it before. Saw it
Yeah.
somewhere just a day or two ago. I don't know much about it.
We're gonna do a search now and get information about it. Here we go. Okay, so the supernova remnant that's known as the Jellyfish Nebula is right here, and this star doesn't have a whole lot to do with it. Okay, so there you see that's what I was talking about. By the way, if we get a bad sighting, then we're not going to be able to stack it, and that's actually quite good. So we had 6.96, 9.38. So there might have been a little gust of wind, which made that just brighter. So we'll let that come in a little bit longer. All right. We got 2 here, then we got a third one. That's pretty. We're actually in the constellation Gemini now, the same constellation for Messier 35. And that's where Propus is, and that's where the Jellyfish Nebula supernova remnant is located. So let's actually darken the background a little bit to kind of bring out some contrast. Look at that. That's gorgeous. You know what, Daryl, we haven't taken pictures of the Jellyfish Nebula with this camera at all. In fact, with the previous camera, we didn't do very many of them. Notice here, we're getting what looks like some green in here. I'm not sure if that's green that belongs here, like here. Hey, Matt Armitage, how you doing? Nice to see you, brother. Thank you for coming in. Daryl, thank you for answering his question, too. I just saw that he asked one.
Yeah.
Yeah, guys, make sure, if you're new to us, darn it all, give us some thumbs up, man. Join our Patreon. Subscribe, it's free. And just hang out with people, most of the people in SkyTour just come here for all the free stuff. We also we do occasional giveaways of telescopes. We just gave away a telescope just a week ago, just before Christmas. We gave away a telescope, and we gave away a pair of binoculars the other day. And that's courtesy of Calybos, who's also in our chat, as well as Tiffany Echo, that's you see in there. Those two are powerhouses, wonderful people that believe in what we believe in, the education of people in astronomy, because it's the rigorous application of astronomy that's going to result in our being able to leave this planet eventually. No, we don't have to worry about it now, but astronomy is a science. I got my degree in that, and astronomy is a science that is absolutely different from many other sciences. Okay, with biology, you can touch the things you're looking at. You can dissect things. You can study them. With oceanography, you can dive into the ocean and take samples. With astronomy, you can't go out there. You just have the light coming to you. And based on the light coming to us, we have done an amazing amount of work. Yes, there's some sample return missions from asteroids and things like that, but this is by far the most amazing science. Now, I'm an astronomer, not an astrophysicist, not a cosmologist. Astronomers tell you what it is. Astrophysicists tell you why it is. And cosmologists say, how could that be, and tell you how it could be. It's kind of a simple way that I mentioned. But I study the structures and the formation of structures out in space. My big thing is dark nebulae. Like you see, there's a dark streak right here. What is that? That's actually a dark object in between us and this obvious piece of nebulous detail here, but that's it. And Daryl's specialty in astronomy is the am I wrong to say it's visual astronomy, Daryl? Is that how would you like that phrased?
That's as good as anything.
Okay, he's a visual astronomer.
I'm an
astronomers
amateur.
huh?
I am an amateur astronomer. I have fooled with photography in the past, but that was back in the days of film. When I look through the telescope, I use my eye, mark one eyeball, and then I try to learn the lore of the sky as well.
Yeah.
The mythology, the legends.
Yeah, if you join us on Sundays from 6 to 8 p.m. Eastern Time, Daryl and I do Sky Tour Radio. This is a Sky Tour live stream. We do Sky Tour Radio on KGRA, KGRADB.com, KGRA out of Ogden, Utah. I'm in Connecticut. The telescope's in Arizona. The station we operate out of is in Utah. And we're on iHeartRadio, Spreaker, a number of different locations. I don't know them all, but there's been TalkStream Live. And Daryl will take you on a what's called a deep dive, where he takes you through the night sky and shows you what's coming up, and we'll often talk about the lore of the night sky as well. So it's really cool, and it's something for everybody. And you know what? You might think that if you're into astronomy as an astronomer, that wouldn't be exciting. It is. It's totally exciting. It's really cool to turn him loose and let him go on and talk about these things. Because he's really good at it.
Well, human history and culture, they have written their stories in the sky.
Exactly.
And that's what mythology is.
Yeah.
As I often say, Homer Simpson saw cowboys in the sky. That's an actual Simpsons episode, too. Homer got a little brother, and Bart got a big brother, and they're jealous of each other. And Homer takes his little brother out under the skies one night, and he says, "There's Jerry, the cowboy." Then he looked over there, and he goes, "And there's Hank, the cowboy." Homer saw cowboys. I mean, the ancients, they saw things they could relate to in their life experience. That's why a scorpion is in the sky. People in Mesopotamia had to deal with scorpions thousands of years ago, and by golly, they saw a big scorpion in the sky. And Scorpius, is one of the oldest of the constellations. It's many thousands of years old.
And it's one of the few constellations that actually looks like what it is, too.
Yeah. I have postulated before, I've seen others do this too, that if you've ever seen the stone carvings over at Göbekli Tepe in Turkey, I've seen speculation that the scorpion carved on one of the columns actually represents Scorpius in the sky.
You could be
That's-
right about that.
Well, I mean, sheer speculation nowadays on our parts, but they played connect the dots in the sky and put their heroes and their animals and their legends up in the sky, and people told the stories night after night, century after century, and that's why we remember them as they are now.
See it? That's what I was telling you, folks. This is why you come here. This is why, because you hear these things. You don't hear this stuff anywhere else. There's people who talk about astronomy, sure, but not while we're doing the universe live in real time like this. This is real time. You're watching this develop right in front of your eyes, and you're hearing about the lore and the backdrop of history from Daryl. So this is the kind of stuff that it's like a TV show. There's people that put this up on their big screens, make popcorn, and watch it like it's a show. It's a very long show, and sometimes we get pretty tired, but it's really worth it. Look at this beautiful object right now. Let me just drop that down. So, this is the supernova remnant. Okay, it's index catalog number 443. It's the Jellyfish Nebula. That's a colloquial name for it. This star is called Propus. Okay, right here. Tejat Prior. Okay, and it's in Gemini. It's Eta Geminorum. That's what the little N means in Greek. Right, but I'm really quite distracted by the detail in this nebula. It's really something else, Daryl.
It's nice.
So yeah. So we'll save this with annotations right now. Okay. Now let's zoom in. Because down here, you'll notice there's a green border. This might be an oxygen filament down here. Not sure. Look at this. That's beautiful. Look at it. Again, with the other camera, this was not available to us. We did not see this kind of detail with the other camera. Look at this beautiful thing in here. This gorgeous, I don't know what you call it. It's a really, really beautiful thing. Spire, nebulous region, area of higher density. This nebula was a lot more generic to us with the previous camera. Now, I'll back out for a minute to show you the whole frame because I want to show you something. The previous camera was 2 full degrees across and 1.5 degrees tall in size. This one is different, and we can show you by going to here, and you can see as we zoom in. Let me actually focus us where we belong. Oh, that's not where we wanted to be. Actually, we're down here. So now we go here. Okay, we're down here by Propus. Okay, so now if we zoom in, you can see written in red, you can see the size of our field. All right, and let me just back out a little. I'm doing more than I wanted. Okay, 1.5 degrees by just about 1 degree. 1.1 degree, 29 minutes by 0.59 minutes. So it's 1.5 degrees by 1 degree. And in that amount of space, we've crammed in more pixels. So in other words, we get more detail. The previous size was like 3680 by 2822, something like that. This one is where's my values here? I just had them. Let's capture profiles. It's in here, I guess. I must have had it. Oh, well, I'm trying to find the size. I don't see it, but It's like 5,800 by 3,600, so it's a lot more pixels that are available to us now for a smaller field of view. So we get that much more detail. It's really something. That's really pretty.
This is just quoting from an article, but just like we saw the neutron star at the heart of the Crab Nebula,
Yes.
there is a neutron star. It's got a long number letter designation, which I won't even repeat. There is a neutron star somewhere in this image that they think was the source of the supernova in the jellyfish, just like the one we saw in the Crab Nebula.
Okay.
It's moving at 800,000 kilometers an hour, though, and it is probably not in the center of the field anymore, and I couldn't find where it actually is.
Okay.
But it moving at 800,000 kilometers an hour, that happens sometimes, you know, when the supernova blows, it blows what's left of the star to the side, you could say, and it's probably still somewhere in this field, but it is probably far from the center of the cloud now.
Yeah, depending how far away it is, you're right. It could be pretty far, or somewhere close by. But look at the fringes along the edge, Darrow.
Oh.
You can see how these fringes along the edge have a distinctly different color. Total detail that was not available to us. This is just incredible. All right, let's say that with the annotations again.
It's about 5,000 light years away, and they think it
Yeah.
happened 30,000 light years ago, or 30,000 years ago. So
Yeah.
that neutron star could have scooted a long way in the meantime.
Yeah. Yeah, so this is beautiful. So we have, let's bring our stack back in here. We've captured a lot of these frames, and we're going to stop now on this one. It's given us time for the other things we really want to see to come up. So we'll save this. Save it exactly as seen. Oops, I screwed up. I can do that, but then I'll just do this. All right, so this will be the Jellyfish Nebula. I forgot to put the name in, but now I'll do it. And yes, I want to change the name. Yeah, I know. It's going to argue with me. Okay. So there we go. So now the Jellyfish Nebula is there. Really great structure in there. Better than we've ever had. That's nice. Let's bring back the telescope. Slide over, please. There's a slight delay because of our internet across the country. Really nice.
Whoops. Excuse me again just a second.
Sure. Okay, we'll come back and we will go into our finder mode. Okay, there we go. And now you can see that this supernova remnant is lost. You can almost not see it. There's a little bit of it here. See a little bit? But not much. Okay, now let's go over here. Back out. Okay. And let's go to this guy. This, right next door, this is a special nebula known as the Monkey Head Nebula. Another region, star-forming region.
Oh, the Monkey Head.
Yeah, haven't seen it for a while, have we?
Yeah, I was about to suggest that. Somebody light up darkness, so it looks like an ape or something. That
Yeah.
made me think of the Monkey Head.
Yeah, there you go. Well, we got it. So we're going to check it out. So you see it says searching, and it's trying to find our guide stars. And it seems to have done so. So we're going to set this to be a 25-second shot as well. You notice 25 seconds seems to be a rule of thumb. Look how much we can do in just 25 seconds. This is something that is just unheard of. How many objects are we doing? Sometimes we've done 15 objects a night. You know? It's crazy. Okay, let's go into our stack now. And let's get rid of our finder mode. And get rid of the stack. And let's see if we... Okay, so our image comes like that. We're going to get rid of this. There's the monkey head. Look at that, guys. Wow. Very nice. And let's color correct. Alright, good. And let's do a quick process. It's going to make it a little brighter. And what we can do is pull ourselves closer up that white curve. That sets our black level. That's why it says black level here. And here you see mid-level. Already developing, and there's only 2 frames stacked. You can see this beautiful dark dust in here, which is encroaching on this nebula. So that's actually up here, and the nebula is behind. All right, you can see how that works right here. Matt says, I see the jellyfish in the previous image. Thanks.
Looks like the monkey head's on fire.
I know, right? James, hi. I don't think I said hi. Well, welcome again. Good to see you. Make sure you guys hit that like and subscribe, man. Because you are what we're all about. Keep us going. Monkey head's looking really nice, actually. Let me zoom in and make sure our focus looks good, too. Let me make sure it looks good. Yeah, we're looking good. Oh, yeah. You notice that in some places you see things like this. Now, those aren't stars with just like gas around them that's ionizing, okay? These are stars that are ionizing the hydrogen gas around them, but from within a dark nebula. This is all dark nebula here. Notice as you move around, you can see hints of other redness, and you also see hints of dark nebula as well. And the biggest hint in this nebula is right here. You can see that. This is a stellar nursery. We're getting in the stellar nursery, we're getting new stars forming in here. Something that was not available to us with the previous camera are the subtle little details we see right here. And these filaments right here, these were not available to us with the last camera. Now they are. And if we move down here, you'll see a slight cloudiness around these stars. And if you look here, you'll see the cloudiness here better. This is a bit of what's called a reflection nebula, that blue stuff I was telling you about. Given time, it might show up that way. And then here you see more. It's blue, but it's all a lighter blue. It's not showing as deeply as some of the other blues we see. So we have hydrogen in here, we have oxygen in here, and we have the dark dust, which is scattering light and making the reflection nebula. You're seeing all 3 of the universe's major lighting mechanisms for nebulae in this one shot. Let's pull up along this a little more to darken it there. That's much better. Now you can see the blue showing up here. That's pretty. All right, we're going to change the name here. Monkey head. Really, really pretty. Let's do our plate solve and identification of our current object. Here we go. IC 2159, NGC 2175, star cluster and nebula. And then you see NGC 2174, the Monkey Head Nebula, which is designated by this circular pattern here. This is not, it will go out of the field sometimes, like this, see? That's what gets saved, that whole thing. So if I say, save annotation, okay, that image gets saved just like you see it. And this list shows you the things that are in it, but you'll see that in here. All right, let's go back to the monkey head. Not live. Really interesting.
I see the mouth, I see the eye. I see his ear over on the left.
Is this the ear?
Farther down. I think that's his ear there.
Okay.
His mouth is the horizontal dark band. The dark patch above is the eye.
This is the mouth?
No. The dark band down below the eye. It's horizontal, the dark band.
Oh, this?
Yes.
Okay.
That's his mouth. And then I would guess that would have to be his eye above that.
Is this like his nose?
And
this is
I don't think he has much of a nose.
Okay, I mean, you might be right.
The eye is closer to the front. He's got a little button nose just above his mouth.
This looks like the line that you see on the monkeys is represented in Planet of the Apes. And is this the nose then?
Nose is to the right. He doesn't have much.
Here?
Doesn't have much of a nose.
Okay. Interesting feature I want to show you here. If we zoom in, look at this feature. That is really cool. We have stars, and the reflection nebula is in here. Really, really interesting stuff.
The big,
so we're looking at
the big diffuse light patch up to the upper right.
This?
No, it's higher up.
I mean,
you remarked on it earlier. There's that right there. The large diffuse patch.
Here?
The white patch, right? It's just above center.
Oh, that.
Yes.
Yeah, okay.
I mean, there doesn't seem to be anything too obvious lighting that up. Oh, I assume it is reflection nebulosity.
Yeah, it's probably so. That's beautiful. I'll tell you, this camera has made exploring the universe even more exciting because we're seeing all the things we photographed before in all new light, so to speak. Or in an all new light. I had to move my heater closer, sorry. Wow, look at that. Oh. Look at this thin filament here. See that thing? This guy right here is really interesting thin filament right here. Just grab that and move it here. That is neat. I do think this is really interesting too, this reflection nebula area right here. That's neat. Wow. Okay, we got 21 captured right now. And the nebula looks pretty good. Let me see what this wants to do. Not much difference. So we're actually pretty close to the processing that it thinks is good. And we can move up a little bit. There's underneath. And then move above. So we've pretty much got the whole nebula here. Now let me back out just to show you. Okay. So this is an area of star formation in here. And that star formation has lit up this area. Okay. This cluster in here is pushing the light gas away, clearing the cavity in here. It's making a hole in this region of space. And to a lesser extent, it's pushing the dust away too. But it's actually, it makes a cavity. That's the big thing. They make cavities in these star clusters. And you don't see them until you look at the nebula up close and personal like this. But there's all dark nebula all around here. And this is just illuminating it with the ionization, reflection nebula, and silhouetting of the dark nebulae in front of it.
Monkey looks like he's up to no good. Looks like he's smirking or something.
Oh, yeah?
You don't see that?
No. I mean, it depends on how I view this. Sometimes I can see the monkey, other times I can't. Let's bring this up. So this is called a push. We're actually pushing detail. And if we come back down here, let this go back where it wants to go. We can actually go to this histogram, this brightness and so forth. And this will show us more data in here. So pretty interesting. It doesn't help you see the monkey any easier, I can tell you that. Huh. All right. I don't know. All right, we'll go to 28 on this, and then we'll move on. Our files have been coming in perfectly now. So this is good. We've had no problems. So it's actually pretty nice out there, Daryl.
Yeah.
All right, we'll save. And then save exactly as seen. I saved the annotation earlier, so we're good there. All right, so this has been saved. So that means it's already racing out of the observatory, heading up to the cloud, and going to get to our distributed server here on skytourlive.org. It'll be up there probably in 30 seconds. Okay, or less. All right, so now let's go back to look at what it would look like in a telescope. If we come in and look at it, we could see some nebula. It might be a little brighter than this, depending on the telescope you're looking through. But like a 6-inch telescope, that's probably what you'd see. 8-inch, a little more. That's my guess anyway. Okay. So now, from the Monkey Head Nebula, we're heading down toward Orion, and we are high enough to see some amazing stuff, including first of the season with this camera, an object known as the Christmas tree cluster. So I believe we'll be able to see that now. So we're going to head that way. This will be our last object for tonight. And as you can see, we have it. And our telescope is high in the sky. Harold Human, how you doing? Nice to see you. This camera that we're using is the ZWO ASI 183 MC Pro. It's a camera that we have been using for about 2 months now. And we used to use the ASI, or the 294 MC Pro. And then we changed to this one because this one is better tuned to this particular telescope. This is a 10-inch system with a Hyperstar by Meade. The Starizona Hyperstar is in place. And Starizona's Hyperstar on this telescope is the only one on the planet, literally. We have the only prototype in the world for this telescope. So, from Meade. You know, you can get a Celestron with a Hyperstar. You can get others. But the only Meade in existence is ours. And it's performing very well. We're very pleased with it.
You can see the Christmas tree. It's upside down. The bright star is the base of the Christmas tree. And then the cluster makes kind of a arrowhead shape pointing down. Top of the tree is right there.
And this is the top right here.
Yes.
That's where the cone is. It's at the Cone Nebula. And further down, we have Hubble's Variable Nebula. I'm going to see if we can... Oh, we can't pull that into view because we don't have the capability with this particular camera. It shows us a tighter view. Remember? So
what are you saying? It's outside the field of view?
Yeah. But I'll see if I can bring it in. There it is. There's Hubble's Variable Nebula right there. Okay. We've been studying Hubble's Variable Nebula every now and then, but I'd like to go back to show you the Christmas tree. The colors in this nebula that you're going to see are... If you thought the other colors were beautiful, wait until you see this. Okay, we're going to move up a little higher because we want to see the Phosphor Nebula too. Alright, and that's another one of the ones that we're going to look at, which is right here. You can't see it yet though. But we're going to drop this down near the bottom because the cone is right here. And this should be good. Let's move a little to the east. And then over this way, I think it's Dreyer's Nebula, isn't it? Isn't that where Dreyer's Nebula is?
Somewhere up there, I think.
Yeah.
Yes.
Ian Kendall, hi, how you doing? Hey, yeah, thanks for popping in, Ian. Good to see you, man. Okay, so we're going to go 25 seconds here. And off we go. You know we're going because you see our progress bar over there on the right. And that's good. Alright, now let's... 25 seconds. Let's bring up our stack. Kyle Lynch is with us. That's Lynn Beats. Nice to see you, Kyle. Thanks for joining us tonight. Kyle hunts exoplanets. What vertical bands? Oh, look at that. Wow. And there's a lot more where that came from. Look at the cone, Daryl. Wow.
Mm-hmm.
That's incredible. Cone, for obvious reasons, called the cone. Wow. Okay, this has got to be a. We gotta drop that down, and we gotta move the telescope out of the way, and let's zoom in on this. And look at this beautiful dark nebula up here. Wow. As you can imagine, this is a region of the universe where we could spend hours digging through the objects here. Hours. Okay, so let's color correct it first. Get a slight correction there. There we go. And then let's process this just to give me some bit more contrast. Look at that. This is amazing. Hey, Mr. Thompson, how you doing? Matt Skrowski, how you doing? The red light at the top of the cone's tripping me out, he says. Yeah, that's a region of dense hydrogen that's ionized by a star or two in the area. It's really cool. But just wait until this comes in a little bit more. The Phosphor Nebula up here has these amazing undulations, and we'll see those in a little while as soon as we get more. How you doing energy-wise, Daryl?
I'm getting a little tired.
All right.
Said this is the last object, didn't you?
Yeah. Kyle, what do you mean binary? What are you asking about? Jeez, this is so pretty. All right, let me change the name here. Christmas tree. It's an open cluster. It's a reflection nebula and emission nebula, all in one. Oh, I see what you're saying. I was pointing at something. Yeah, I wasn't pointing at the stars per se, but sorry if I confused you. Let's look at the top of the cone here. Well, look at that. We got the two stars really nicely there. There, look at that. We didn't get those resolved before. You can see them now. Wow, that's something. Let me try something. Let's go to our enhancements. Let's take this color correction and move it up to 8. Yeah, so it removes more of the color noise that was in there. Wowee. Holy cow. Beautiful. Ah. So the Phosphor Nebula is starting to show some detail in it now. This beautiful blue reflection nebula. There's dust all throughout this region. And in the final processed version of this, you can see an incredible amount of dust all through here. This is like a big dark lane of dust. This is a big dark lane. You know. Incredible. Here's a beautiful dark patch up here, denser. Wow. I am really finding this fascinating. First time we've taken this image with this camera. This has never been done with this camera before. This is the very first time. In this one image, you've got everything. You've got the blue reflection nebula. You have got the red emission nebula. You've got the dark nebula. And then you have, now you see these undulations showing up now. You can start to see the cloud structure of the Phosphor Nebula. Right in here. You can start to see it. So it'll click in here in just a sec. There you go. You can start to see there's detail in here. Wow, that's pretty crazy. Really pretty. And that's like a brownish dust that's being illuminated by stars in the area. Look at that. And you're all welcome to take these images from our server here at skytourlive.org and play with them yourselves if you want to. Ronald says there's a lot to see. That's ERRT radio. Radio. You know, the longer we go, Daryl, the more detail you can see just coming out everywhere.
Uh-huh.
There seems to be a dark lane right here. I think it's pretty interesting.
Thank you, Harold.
Oh, Harold, thank you, man. Thanks for joining us, Harold. And, you know, if you want, you could actually, like I said, it's free, so please join. You know. Harold, where are you from? Kyle says, just seen your show on Hulu a bit ago. Here this weekend, heard a familiar voice, and I said, wait a minute, that's Mark. Yeah. I guess some of the stuff I've been in is on Hulu. If you want to see what I do in astronomy and video and image processing, you can look at History Channel. My current show I'm on is The Proof Is Out There. It's an A&E network station. That's History Channel. So you could enjoy that if you wish, or make fun of it. Throw stones at me if you wish. You know what, Ronald asked, when is it on? You know, I should know, shouldn't I? I never get to see my stuff, so I don't know. You're in Gastonia, North Carolina? Harold? Oh, cool. No, Ronald, it's not that. They would give me the show dates if I asked them. And you can look it up online and find out when it appears on History Channel. I just filmed another whole, they're called tranches, a whole tranche of stories with them. 3 out of 4, and they're going to come back and we're going to do a 4th set. They used to come out once a year. That changed to twice. Now they're doing 4. And then they actually look like they're having me in another show. I've already done some of that recording. That's another cool, it's a cool quick hit. It's like a 60-second thing. But then there's more to come that I'm not going to be able to mention that are thinking about. It's a very progressive network. They got a lot of balls in the air and a lot of really cool stuff. So, you know. Yeah, Kyle, I know you'd love to do these shows and stuff about exoplanets and stuff. But, you know, they're going to have exoplanet scientists on there that have been doing it for like 25 years. So you would come in probably, I would think, as one of the research assistants that has worked on identifying transits in some of the data. I think that would probably be something you could do. And I think you'd do a good job with that. Hey, Raymond Bobel, I haven't seen you in a while. How you doing, Ray? So nice to see you. I'm so glad you're following along. I was going to give you a call, find out how you're doing. You know, Ray has been a staunch supporter of SkyTour Livestream for a number of years. So it's nice to see you come in, Ray. Really nice to see you come in. Okay, we're up to 27 stacked here, Daryl.
Yeah.
Look at the Foxford Nebula now, guys. See that? We'll zoom in. As you zoom in, the color changes a little bit because the screen has to be allowed to sort of catch up. All right. So now it's caught up, and you can see now all these little subtle variations in the brightness in here now. See that? A little nice reflection nebula circling over all this. Hey Z-Bike, how you doing? What's up, man? Okay, let's get the telescope back here and bring up we'll dock our system here. Okay. Very nice. Wow. Interesting how you got this dark band in here, Daryl. Wow, that's amazing. Kyle, thank you for the well wishes. Happy New Year to you too, my friend. It's weird, you know, I do this on many clear nights with you, Daryl, and it still amazes me that this telescope right here that we're looking at is 2,500 miles away from here, out in the Arizona desert, in the middle of nowhere, and I've got pretty high-speed internet out there, courtesy of Starlink, and you know, full access to all the mechanisms in there. It's pretty crazy. I mean, it took me a year to figure all that stuff out and get it up and running, and I did it here. The telescope, not this telescope. Well, actually, this telescope. The systems took a year, and the telescope used to be 75 feet away from me in the front yard, or 100 feet away, and I moved everything to Arizona, and behind me right now, I have the old telescope, the previous telescope that was here, that we're going to put it back in the East Coast, and then we have the new telescope, second new telescope that's going to go out into Arizona in another location. So let's see what Z-Bike says. Seeing this channel reminds me of my days in Chile when I had my telescope and I spent hours looking. Now in Miami, I don't see anything. Oh, you know what? It's true, you know, light pollution. But I'll tell you this. We're using special filters. And these filters, although they're cutting through and showing us only the light we want to see, you could use these same filters in Miami and get an image a little less well defined than this, but with the right filters, you could actually do this in a very bright region. It would take you a lot longer, and you'd have to do something called narrow band imaging, which you may already know about, Z-Bike. And the narrow band imaging would allow you to capture this in very brightly lit, light polluted areas. We have a filter that's a little more broadband, and we're actually doing it in one shot. We're not doing separate exposures and then combining them like you would do with narrow band imaging. Narrow band is not difficult in Bortle 6-7 skies, Kyle. It's actually how you would do it. And there's a guy called Astro Backyard that does narrow band imaging in Bortle 6-7 skies. And Bortle is for those of you that don't know, Bortle is a brightness, a sky brightness indicator created by John Bortle years ago. Bortle 1 and 2 and those low numbers are very, very dark skies. What you see here, this is a Bortle 3 sky, Bortle 3.5. And Bortle 7, Bortle 8, 9 skies, those are the types of skies you get in the middle of a city. Okay? But with the proper filters and use narrowband filters, you only get that exact slice you want. So all the light pollution's throughout, but if you get this little narrow band slices, you can take the data and build it up and make your images. And you could get, you could actually get better results than this with narrowband. And if I wanted to spend 4 hours doing it with you guys, we could do it. But then I'd have one person watching, and it would be Daryl, if that, you know. So anyway, that said, here's our Phosphor Nebula. Notice it has texture and a lot of real nice features now. Let's see if we can draw out a little more data. Yeah, look at that. Now you can see the cloudy nature of the Phosphor Nebula as it overlays this reflection nebula. Nice, thin, beautiful tendrils. Again, stuff we've never had available to us. Then down here, the Cone Nebula, as I said, named obviously. But look at that. Wow. Calybos, yeah. Yeah, you're in awful land when it comes to astronomy, but with narrowband filters, you too could create some miracles yourself. Wow. Okay, we've got 41 shots done here. I'm going to save these now. And 42. Good. Oh, I did it again. Or did I? No, I got that. I did the Christmas tree. Okay. So we got that. And we're going to save it exactly as seen. Then we'll do our identifier. Yeah. And we're going to do our search here again. And we'll see what we get. There we go. Okay. So now you can see Christmas tree cluster, star cluster, and nebula. And it doesn't list everything. That's coming. But it's not listing everything, unfortunately. Now, 15 Monoceros is the name of that star that we're seeing there. And then the Christmas tree cluster is the cluster associated with that. Yes, Kyle, that's Lynn Beats. Yes, Kyle, it's plate solved on the fly. Okay. Let me just save this. All right, so the image will come up and say it's saved. There we are. And what's getting saved? I'll show you. So this is the image with anecdotes that's saved. We'll take a look at what that looks like. See? So that's what you get. So now it'll help identify what you're looking at. Pretty cool. All right. Wow. I am just amazed, Daryl. This is really beautiful.
Yes, it is.
What do you say? Just one more? Do the Hubble's Variable Nebula down below?
If you like, sure.
Okay. Just one more. We won't do nearly as many images, but
Yeah.
we do like to do the Hubble Variable Nebula precisely because it's a variable nebula. Now, we'll showcase all the things we can see in here for you. That's beautiful as it is, but you'll be able to see even more of that. So we'll go back to our 1 second finder. And there we go.
Moonrise in about 16 minutes.
Yeah, so that's why I want to get to Hubble's Variable Nebula now. Oh, shoot. I need to, I probably already have it in here. Okay, so it's a little further down. There it is. Now, remember all the black dust I told you about, guys, in here? This black dust is responsible for filling this whole region. And in this particular case, we have this little nebula that shows up out of nowhere. It looks like it's just a nebula in the middle of space. It's not. It's actually a reflection nebula that is lit up by a star, and it's an area inside dark nebula all throughout this, and it just happens to be sticking out enough to be seen, and that's what we're looking at right here. So we're going to just do a quick set of shots on this one, right, to kind of showcase Hubble's Variable Nebula for you. We've never done it with this camera, which is why I want to do it now. And I am usually Mark, just one more, D'Antonio. That's what people will say. Just one more. And we'll do 25 seconds. Even that's going to be too much. But we'll check it out. And we'll go into our live stack here. That's beautiful. This is the previous one. It's all saved out there. So we'll clear it now and bring in Hubble's Variable. And you'll see other red nebula up here that begin to show up. Okay. Look at that, Daryl. Look at that. Holy cow. And we're seeing more detail in this than we've ever seen before. Look at that. Wow. That's really cool.
Refresh my memory. This is the one where we see changes in very short order.
Yes, you and I have seen changes in this.
Yeah.
And what's happening is there's a star you can't see, and it's responsible for the nebula varying in brightness. And if you notice, you're looking into, there's all dark nebula in here. There's a star in here. Okay? As we zoom in and gather more images, you'll see that there's stars, and there's like, this looks like one right here. That's actually not doing it. It's a star that's buried inside this dark nebula here. Okay? And we're going to see more details showing up here in short order. It's really something. Now, because we went down and because we still have you already see red nebula here. We actually will probably not be able to mosaic these together because the camera doesn't allow that for the size field difference, because we're too far down to actually mosaic. We have to do one more in between. Look at that. This is stunning. This little thing.
You can see dark modeling in it.
Yeah. Okay, let's go back here. Okay, there's Hubble's Variable Nebula. It's a reflection nebula. Now, it varies in brightness because the star that's inside this nebula apparently has dust orbiting it. And as it orbits the star, sometimes more of the dust gets in the way and dims the nebula a little, and then it comes out and brightens it up. So that's incredible. You know? Calybos, you don't have to apologize. You're a mainstay with SkyTour Livestream now, along with Tiffany. As I've said before, earlier in the broadcast, I mentioned we give away telescopes and binoculars, and eventually night vision system that we're working up to. For that, you'll need to be a member of our Patreon. But we gave away a telescope already to JSCO 77. We gave away binoculars to Mind Remote 7 the other night, and she already got them. So we're not fooling around. And when we say we, I mean me, Daryl, Calybos, and Tiffany, and Marianne, and Tara. We're all part of the SkyTour phenomenon. And Calybos and Tiffany are responsible for the entire product giveaway segment of what we do. They've asked us to kind of be their distribution arm for this, and I think that's really good. Hey, look at Ronald wants the see that? Calybos and Tiffany, Ronald wants the Celestron binoculars too. Our Raza system is good. Nice thing about the one we're using is we can easily convert it from this F2 back to the F8. It would be a 5-minute conversion if it was nearby. So if we had that out here in the front lawn, we could do a wide angle shot and then convert it in 5 minutes to go back to its native F8. But for remote telescopes, well, you are stuck with what you get, you know. Look at this. This is pretty. Okay, we did 11 exposures so far. And just a few more. Let's see if we can get some details. We zoom in here. Wow. When I was at the university, one of my targets was the Hubble's Variable Nebula. I photographed it from a Bortle 6 sky, and I was able to capture it kind of like this because I was using a 20-inch refractor to do it. 20-inch Alvin Clark refractor. It was over 100 years old. But boy, was that a great telescope. Still is. I did lots of work on that telescope, working on a parallax program, which studies the distance to nearby stars. I looked at Blur X of Blur 10. I'm not sold on it yet. That's Kyle Lynn Beats is asking me about that. Okay, we're going to go to 15 exposures and call it. This is our bonus object for the night. Let's see if we might go beyond 15 though if I'm doing this. I want to see if we can find out where we are, see if it recognizes Hubble's variable nebula. It should. I would think it should. Yeah. There we go. Nice. So we'll save the image with the anecdotes and annotations. Very nice. Okay. Yeah, it's a Caldwell object as well. Okay, 15 done. We're going to save this. And then we're going to save exactly as seen. And there you go. Well, there you go, ladies and gentlemen, and everybody. Excuse me. Once again, you've wasted a perfectly good evening with us. We hope you had a good time here tonight. All the imagery we took tonight will be available right there at skytourlive.org. So don't miss it. It's over there. Okay, skytourlive.org. You can't miss it. Raymond B., thank you so much. And it's really good to have you back, Raymond. I've been wondering how you've been. You know, how are your craters doing? If I recall, you got a Mars and a Moon from us that we sent crater plates out to you that we 3D printed. You know? Yeah, Ronald, you get 6 figures but all zeros. Wow. I'm glad it was never a wasted evening. Well, since we waited so long, I guess I'm going to get 20 exposures now. Yes, your Andromeda was done. And your double cluster is done as well, Ronald. Ronald being in the Patreon, he's at a level that affords him the ability to come on and drive, basically. So he did that. Thanks, Z-Bike. Oh, Atacama, yeah. Alma, yeah, the sub-millimeter telescope. Oh, yeah. I think that is a phenomenal system out there. In fact, that system is responsible for a lot of discoveries. You know. Thanks for mentioning that, and thank you again for the contributions, Z-Bike. That's wonderful. Really, really wonderful. Thank you. Okay. Well, there you go, folks. Thank you so much for coming, and had a great time. Bonnie on Ahata 77, thank you so much for coming. It's been great to see you as well. And we will be back on other clear nights. There are so much more to explore. We haven't even looked into Orion yet. Okay. At least not terribly officially. So that we will do. Let's go back to this and before we head out here. All right. Okay, guys. Well, thanks so much for coming. Really appreciate your attendance and your patronage. And we'll talk to you very soon. I'm going to be heading to bed myself. It's just about 1 a.m. here. Daryl's, you're about 2 hours behind me, right?
Yep.
Yep. But you get up early in the morning, so, you know, you're probably tired as well. I get up a little bit later. So, we're going to take a break for tonight. Fantasy, good to see you, by the way. And we'll talk to you again. So, have a good night, everybody.
Good night, everybody.
See you later.